Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about engineering tribology subject. So the today's topic is corrosion. So already we have studied about corrosion and what is the importance of corrosion in engineering tribology and how to prevent corrosion. These topics already in previous session we have learned. The today's topic is I want to discuss about theories of corrosion and the types of corrosion. So in that the theories of corrosion already one theory we have studied in previous session, and the second other types of theories we will see in today's topic, and then the types of corrosions also we will study. So the introduction about corrosion already you know. So once again recall the introduction of corrosion. Any process of deterioration, that is destruction and consequent loss of a solid metallic material through an unwanted chemical or electrochemical attack by its environment starting at its surface is called corrosion. So the corrosion means this is a not important process. It is unwanted thing due to this unwanted chemical reaction with the with metal when it is exposed in atmosphere environmental conditions. Some material loss will be happen. So this the deterioration destruction of material is called as corrosion. So that's why the corrosion is a process reverse of extraction of metals. So extracting the metal means we are gathering the metal from various sources, but this corrosion is destroy the metal. So that's why this is a reverse of extraction of metals. Coming to the theories of corrosion point, there are two theories of corrosion. So already we have seen in the previous session direct chemical corrosion and dry corrosion, and electrochemical corrosion or wet corrosion. So two types of theories are there. One is dry corrosion or also called as direct chemical corrosion. The second one is wet corrosion and also called as electrochemical corrosion. So we will discuss one by one. So dry corrosion or chemical corrosion means they mainly through the direct chemical action of atmospheric gases. So like oxygen, halogens, H2S, SO2, N2 or anhydrous inorganic liquid with the metal surface. So the direct chemical action of atmospheric gases with the metal surface. This type of corrosion phenomena is called as chemical corrosion or dry corrosion. Again, this dry corrosion classified into three types: oxidation corrosion, corrosion due to other gases, and liquid metal corrosion. So all these things three already you have studied in previous sessions. So now we will see the wet corrosion or electrochemical corrosion. So what is this wet corrosion? This type of corrosion occurs where a conducting liquid is in contact with the metal. So that a conducting liquid directly contact with the metal, this corrosion occurs due to the existence of separate anodic and cathodic parts between which current flows through the conducting solution. So this is the phenomenon of the wet corrosion. That at the anodic area, oxidation reaction occurs, thereby destroying the anodic metal either by dissolution or formation of compounds. Hence, corrosion always occurs at anodic parts. The anodic parts, there are two parts are there, anodic and cathodic. So the reaction, the oxidation reaction occurs there by the destroying the anodic metal. So the always the corrosion occurs at anodic parts. So whatever the conducting the liquid used that is in contact with the metal, there the wet corrosion is possible. So the due to the existence of separate anodic and cathodic parts between which current flows through this conducting solution. So that is the main concept of this wet corrosion or electrochemical corrosion. So the mechanism of wet corrosion is the electrochemical corrosion involves flow of electrons between anode and cathode. So the flow of electrons transport between anode and cathode. The reaction we will see in this slide. The anodic reaction involves dissolution of metal and liberating free electrons. So take example this manganese, and so here the cathodic reaction consumes electrons with either evaluation of hydrogen or absorption of oxygen, which depends upon the nature of the corrosion environment. Clear? So evaluation of hydrogen, this type of corrosion occurs in acidic medium. Example, considering the metal that is iron Fe ferrous in acid solution, anodic reaction is a dissolution of iron as ferrous ions with liberation of electrons. So the evaluation of hydrogen example in acidic medium, the metal iron in acid solution, anodic reaction is dissolution of iron as ferrous ions. So liberation of electrons like already shown in this equation. See the anode reaction ferrous, the ferrous 2 plus ions and plus 2 electron minus. That is oxidation. The electrons released flow through the metal from anode to cathode. So whereas H plus ions of acidic solution are eliminated as hydrogen gas. So that cathode, see H plus 2 hydrogen plus 2 electrons, that is the reduction, it gives H2. So the overall reaction between this ferrous and hydrogen, the Fe plus 2H plus, you can write Fe2 plus H2. So like this, the oxidation at cathode, the electrons released flow through the metal from anode to cathode. This type of corrosion causes displacement of hydrogen ions from the solution by metal ions. Here displacement of ions, hydrogen ions from the solution. All metals above hydrogen in electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evaluation of H2 gas. The anodes are large areas, whereas cathodes are small areas. So this is important observation here. The anodes are large areas and cathodes are small areas. The reaction between these, the electrons flow happened between anode to cathode. The absorption of oxygen. For example, rusting of iron in a neutral aqueous solution of electrolytes in the presence of atmospheric oxygen. Usually, the surface of iron is coated with a thin film of iron oxide. If the film develops cracks, anodic areas are created on the surface. While the metal parts acts as cathodes, it shows that anodes are small areas, while the rest metallic parts from large cathodes. So the released electrons flow from anode to cathode through an iron metal. This is the example, the rusting of iron in neutral aqueous solution of electrolytes in presence of atmospheric oxygen. So how the reaction happened between these two ions, two metals. So the main difference between this dry corrosion and wet corrosion. Already we have seen the chemical corrosion. We have seen the reaction in chemical corrosion or dry corrosion. The second one is electrochemical corrosion, that is called as wet corrosion. So the first observation is difference is it occurs in dry condition, not in liquid metal. You are not used any electrolyte. But the electrochemical corrosion occurs in the presence of moisture or electrolyte only. So the compulsory the electrolyte is required for the electrochemical corrosion or wet corrosion. But in this case, it happened in a dry condition. And also the second difference is it is due to direct chemical attack of the metal by the environment. But it is due to formation of large number of anodic and cathodic areas. We have seen in previous slides. Is the dye corrosion happened due to the direct chemical attack of the metal by the environment. Some gases attack directly with the metal. Even a homogeneous metal gets corroded in this dry corrosion. Heterogeneous bimetallic surface alone get corroded. But in this case, the wet corrosion, the homogeneous metals not corroded, so not possible to corrode. But only in wet corrosion, heterogeneous bimetallic surfaces alone get corroded. It is a self-controlled process. So it is a continuous process. The wet corrosion is continuous process, but the dry corrosion is a self-controlled. And one more difference is it adopts absorption of mechanism. It follows wet corrosion, but it follows electrochemical reaction. So in this, it adopts the absorption mechanism, but in this it follows, not adopt any mechanism. Formation of mild scale on iron surface is an example. Rusting of iron in moist atmosphere is an example. In wet corrosion, the rusting of iron in moist atmosphere conditions. This one mild scale iron surface is an example in dry condition also due to the some gases at a direct contact with the metal. This type of chemical corrosion will be happen. But in this wet corrosion, not like that. Suppose your iron, any metal exposed to the moist atmosphere conditions, the compulsory the rusting will be formed. So this is the example for this wet corrosion. So these are the main difference between this dry corrosion and wet corrosion. Next, coming to the types of corrosion. Up to now, we have seen the theories of corrosion and then the types of corrosion. So, different types of corrosions are there. The first one is galvanic corrosion. The shown diagram here, the bolt and nut. So, the brass screw, the cathode protected, and a mild steel nut, anode undergoes corrosion. So, you can see the rusting of metal, the nut. So here two different the metals are there. One is screw material is different and nut material is different. The combination of these two metals gives the corrosion, the bimetallic corrosion, that is called as galvanic corrosion. So how it happened? So you will see the galvanic corrosion means when two dissimilar metals are electrically connected and exposed to an electrolyte. Whenever these two bimetallic metals are exposed to an electrolyte, the metal higher in electrochemical series undergoes corrosion, and the metal lower in electrochemical series, that is high reduction potential, is protected. This type of corrosion is called as galvanic corrosion. So this is the mechanism behind this galvanic corrosion. So whenever two dissimilar metals are electrically connected or exposed to an electrolyte, so there must this type of corrosion will be happen. Example, take example, zinc and copper are connected and exposed to corroding environment. So the zinc higher in electrochemical series forms the anode, the undergoes oxidation and gets corroded. Copper lower in electrochemical series acts as cathode, undergoes reduction and protected as the electrons released by zinc flow towards cathode. So there is a the reaction between this anode and the cathode. The electron flows from zinc to the copper material. So this is the example for galvanic corrosion. I will show you the diagram. So in this, see the anodic metal zinc added electrons, and the cathodic metal reduction, electrons are reduction here. See the two metals, one is copper, another one is zinc. So exposed to an ultralight. These two metals are connected, and so the electronic current is there, is shown in diagram. So here anode to the cathode, the electron flows are there. So here see, here here the undergo the cathode, at cathode the undergoes reduction of material and is protected as the electrons released by zinc and copper. The electrons are released from zinc materials towards copper. Next, prevention of galvanic corrosion. How to prevent this type of corrosion? Can be avoided by coupling metals close to the electrochemical series. So whenever you have to assemble two metals, you must see that those metals very close to the electrochemical series. Not one is higher, another one is not lower chemical series. Somewhat close to electrochemical series. So by using this technique, you can prevent this type of galvanic corrosion. Next, fixing insulting materials, insulating materials between two metals. So here, some materials, the fixing the insulating materials between these two metals, you can avoid this type of corrosion. Using large anodic and smaller cathodic metal. There are ways use anodic and smaller cathodic metals you can use. The examples of galvanic corrosion are steel pipe connected to copper plumbing, zinc coating on a mild steel, etc. The example for the galvanic corrosion. Next, second type is concentration cell corrosion. This type of corrosion occurs due to electrochemical attack of the metal surface exposed to electrolyte of varying concentrations or varying aeration. So that means so not constant electrolyte, not constant electrolyte, not constant concentration of electrolyte. So the electrolyte also vary with different the concentrations or varying aeration. This type of corrosion is due to the difference in concentration of metal ions. So whenever there is a difference between the metal ions, the concentration wise, there must corrosion will be happened. So that corrosion is concentration cell corrosion. This corrosion happened due to the concentration difference between these two metals. The difference in the exposure to air or oxygen, differential aeration corrosion, difference in temperature due to the difference in oxygen, due to difference in temperature, due to the concentration, this type of corrosion will be happen. So example here shown in this diagram. See the zinc rod, the water line dipped into this water. So less oxide, the oxygen generated part, corroded anode, that is zinc gives zinc 2 plus and 2, already you know this equation, Zn2 plus 2 electrons, here NaCl chloride solution here, and then the more oxygenated in the part cathode. So the cathode here half of oxygen reacts with water and it gives 2 OH, so hydrogens. So this is concentration cell corrosion reaction. You can you can show like this. So the differential aeration corrosion is the most common type of concentration cell corrosion. When a metal is exposed to different air concentrations, similarly the metal liquid concentrations, the air concentrations also uh, plays important role in this concentration cell corrosion. It has been found to be poorly oxygenated of the metal becomes anodic and well oxygenated part becomes cathodic. The potential difference is created which causes the flow of electrons from anode metallic part immersed in a NaCl solution to cathode exposed to atmosphere. Example, zinc rod immersed deep in a NaCl solution, that is anode. The zinc rod above NaCl solution, that is cathode. This is the example for concentration cell corrosion. The zinc rod immersed deep in NaCl solution, that is act as a anode. Zinc rod above NaCl solution is cathode. In previous diagram, one is anode or cathode and another one is the zinc rod act as a cathode. Sorry, anode. At anode reaction, you can write like zinc, it gives Zn2 plus 2 electron minus oxidation. At cathode, half of the oxygen plus H2O plus 2E minus 2 electrons reduction and 2 OH. So overall reaction you can write like this. The Zn2 plus and 2H ions interact to give Zn oxide, thus corrosion occurs at anode. Next third one is waterline corrosion. This is also known as differential oxygen concentration corrosion. So it has been observed in the case of iron tank containing water that the portion of iron tank just below the water level undergoes corrosion. It is due to the difference in oxygen concentration. The portion of iron tank just below the water level undergoes corrosion, not above the water level, not happened any corrosion. See, it is mainly occurs due to the difference in oxygen concentration. Different oxygen concentration levels are there above and below the water level. The area above the water line, highly oxygenated, acts as cathode and is not affected by corrosion. However, if the water is reacted free from acidity, little corrosion occurs. This type of corrosion is prevented to a great extent by painting the sides of the ships by anti-fouling paints. So this is example for waterline corrosion. So you can see here highly oxygenated cathodic part above the waterline. Poor oxygenated anodic part is corroded. It is below the waterline. One is below and another one is above the waterline. So the waterline corrosion equations at anode, you can write Fe, it gives Fe2 plus 2E electrons minus, and at cathode H plus half of the oxygen plus 2 electrons gives H2O, and again this H2O gives H plus OH minus. This overall reaction you can write like this. If the oxygen in excess, the ferrous oxide is easily oxidized to ferric oxide. So the ferric hydroxide, this 4FeOH3 is called as ferric hydroxide. The product called yellow rust corresponds to this Fe2O3, 3H2O. Next one is pitting corrosion. The pitting corrosion is due to the crack on the surface of metal. There is a formation of a local galvanic cell, pinholes, pits, and cavities in the metal. So sometimes the cracks occurs on the surface of the metals due to the irregular stress distribution in the material whenever it is subjected to load due to the poor stress concentration. There are many cracks occurs on the surface. Due to this crack on the surface, there is a formation of corrosion. That corrosion is called as fitting. Corrosion local due to the formation of a local galvanic cell. The pitting is usually the result of the breakdown or cracking of the protective film on a metal at a specific points. This gives rise to the formation of small anodic and large cathodic areas. In the corrosive environment, this produces corrosion current. So you can see the pitting corrosion diagram. So the electrochemical reactions that occur when a pit is initiated at a sulfide inclusion in a carbon steel. So here shown the nature of the neutral aerated NaCl solution, the occasional bursting of crust due to hydrogen evaluation, porous crust. So uh, this is the diagram for this fitting corrosion. You can see, you can observe the equations of anode and at cathode reactions. The detailed diagram, the corrosion product, the more oxygenated cathode and the more oxygenated cathode equation you can write like this, and anode is attack. You can write here ferrous gives 2 plus 2 electron minus ferric hydroxide finally occurred. At anode equation you can write like this: oxidation and reduction and overall reaction. The product called yellow rust corresponds to ferric hydroxide. Next one is fifth one is intergranular corrosion. This is the last type of corrosion. This corrosion occurs along grain boundaries. So the grain boundary where the metal is sensitive undergoes corrosive attack. The grain boundary contains a material which shows more anodic potential. In every metal, it has some grains, sometimes very closely packed, and sometimes they distribute with uniform space, and sometimes irregular grains also. You can see the grain structure under microscopic test. So whenever the grain boundary with the metal is sensitive, there the the boundary grains are not in uniform uniform state. There some corrosive attack is possible. The metal at the grain boundary decays as it becomes anodic, and the center of the grain becomes cathodic, which is protected. The center of the grain is becomes cathodic. It acts as cathodic. The grain boundary at boundary it becomes anodic. So there is a reaction between this anodic and cathodic. It gives corrosion. That type of corrosion is called as intergranular corrosion. So you can see the diagram here. The grain center cathodic, the grain boundary anodic. This is one grain, and the second, third, different like this different grains you can observe in the metal by under examination of microscope. You can see grain structure of the metal with the help of microscope only. So due to this internal granular structure, the corrosion also will be occurred on a metal surface. This is one type of the corrosion, that is intergranular corrosion. So that up to now we have learned the theories of corrosion and then types of corrosion we have studied. So these are the references I have taken. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.